We're evaluating dy over dx.
Okay.
And then
Do they give you
and
the
it's of
function?
the equation. Sorry, it's of the equation sine y equals x when y equals 0.
Hold on. Let me start from scratch.
Oh.
What's the equation?
It just says evaluate dy dx of the equation sine y equals x. So
Okay.
sine y equals x.
Okay.
Yeah.
So if we have to do implicit differentiation here. Okay?
Okay.
In other words, we're going to take the derivative relative to x of both sides.
Okay.
Okay? As long as I do it to that side, I got to do it to this side.
Yeah.
What does the left side become?
Well, sine y, I'm still a little confused on this whole y stuff. That's why I'm.
Okay?
That's.
When you are doing implicit differentiation, and you come across a variable that is not the denominator variable, in other words, it's not x, then you explicitly differentiate that, becomes cosine y, but you have to follow it with a dy dx.
Okay.
Only because y is not x. Okay? When I do the right side, that's x, so the derivative is 1. And I don't have to follow it with a dy dx or a dx dx.
Okay.
And that's really the only rule you have to memorize. Okay, so in this case, dy dx is 1 divided by cosine y, or you could say dy dx is secant of y.
Okay. All right.
Okay, let me just, I'm sure you'll have more problems that illustrate this, but let's just take this equation right here. The equation of a circle. And I want to find dy dx. Okay, so I'm going to take the derivative of the left relative to x, and I'm going to take the derivative of the right relative to x. Well, when I get to the x squared term, that's just 2x. I can explicitly differentiate it. Only because x is the same variable as that x. I don't have to follow it with anything. But when I get to the y term, I have to explicitly differentiate it, and because of the chain rule, I have to follow it with a y prime, dy dx. And if the right side is 0, and if you solve this, you get y prime equal minus x over y. Now, here's one of the major differences between explicit and implicit differentiation. When you explicitly differentiate something, you almost always end up with a function of x. When you implicitly differentiate something, you usually end up with a function of x and y. So if you want to find the slope at a given point, you need the x and the y coordinate.
Okay.
In other words, I would not be able to evaluate y prime if you just told me the point was x equal 2. Well, I kind of could, because I could go up and plug it in here and figure out what y was equal to. So I would be able to in that case. But usually when they ask you to evaluate the first derivative at a point, they'll give you the x and the y coordinate, and you plug them both in.
Okay. All right.
So that's implicit differentiation. I'm sure you have more problems that are that. It's actually fairly easy once you get it, once you understand it. What do you got else?
So the next one is for problems 11 and 12, use f of x equals the cube root of x squared minus 1 squared.
Like that?
Yeah. Uh-huh.
And the only
And
reason I
then,
wrote it as a fractional exponent to the 1/3,
right.
because when you're doing calculus, it always makes sense to do that.
Okay.
Okay?
Then we have to find
In other words, radical signs don't help you since you're always using power rule and stuff like that.
oh, okay. All right.
Okay?
And then we have to find where f of x has a horizontal tangent and where it has vertical tangent.
Okay? Let's first of all find f prime of x. How can I first of all simplify that function?
Well,
You sure I've written it precisely the way it is?
well, I mean, they didn't do what you did with the thing, but yeah, it's
Okay. So
yeah.
I can multiply the two exponents here. So
Okay.
what I end up with is x squared minus 1 to the 2/3. It's the
Okay.
same as the cube root of x squared minus 1 squared.
All right.
Okay? And so it's easier to find the first derivative if I write it like this. So
All right.
what is the first derivative?
Well, now it's gonna be 2/3 x, or no, 2/3 2x, and then
No,
negative 1/3.
don't change. In other words, you have to apply the chain rule here.
Oh, right.
And
Okay.
the chain rule says you take the derivative of the outside and you multiply it by the derivative of the inside. Well, so the first step is let's take the derivative of the outside.
And then negative 1/3.
And then I'm going to multiply that by the derivative of the inside.
Okay.
So that's f prime of x. And let's write it a little nicer. Put that in the denominator. So I can multiply the 2 times 2, so I have 4x in the numerator.
All right.
I have 3 times x squared minus 1 to the 1/3. That's my f prime.
All right.
Okay? It's asking for horizontal tangent lines.
Yeah, and then later on vertical tangent.
Okay? What makes for a horizontal tangent line? The first derivative of what?
0, right?
Okay? So if I have a rational function or a rational quotient that's equal to 0,
Mm-hmm.
the only thing you really need to care about is the numerator, because the only way this thing can be equal to 0 is if the numerator is equal to 0. Notice I can multiply both sides by this.
Oh, right. Okay.
And I have to have 4x equals 0. So x equals 0 is a horizontal tangent line.
Right.
And where do vertical tangent lines come?
Um.
When the first derivative is what?
Ooh. I guess it would be 1. Or wait, no, not 1. No, infinite.
Infinite.
Yeah.
Which comes when you divide by 0.
Oh, right. So now you only care about the denominator.
Exactly. What
Right.
makes the denominator 0? And that's what would make that first derivative infinite or undefined.
Mm-hmm.
It's only two numbers.
Well, 0. Wait, no, 0's not 1. 1. 1 is 1.
Okay, x equal 1. What else?
And then negative 1.
Negative 1. So you have two places where you have vertical tangent lines, and you have only one place where you have a horizontal tangent line.
Okay. That makes sense.
Let's see, that was both questions for that
Yes.
one function? Okay.
Yeah. The 2 response down there. Then I have find the slope of the tangent line to the graph of 4x squared plus y squared equals 5.
Not that different from my example.
At the point 1 comma negative 1.
Notice they give you both the x and the y coordinate.
Uh-huh.
Because when we implicitly differentiate this, we're going to have a function that is a function of x and y. So let's implicitly differentiate this. In other words, the first thing we need to do is come up with dy dx. That's going to give us the slope of the tangent line.
Right. Okay.
Okay? Implicitly differentiate that term.
That's just 8x.
What about the next one?
And that's going to be 2y times y1.
Yeah, it might be helpful to write it as dy dx in this case.
Oh, okay.
Right? So, only because when you're talking an implicit differentiation, it matters a lot what that denominator is. So the dy dx notation is more valuable than just y prime. Y prime doesn't tell us what we're differentiating it with respect to.
Okay.
What's the right?
0, right?
Huh? So now solve for dy dx. What do you get?
Yeah. Sorry, I'm just taking it. It's just negative 8x minus 2y.
Negative 8x divided by 2.
Oh, sorry.
Which
yeah, because multiplied by,
yeah, because 2y is a multiplier.
Mm-hmm.
Okay, so that becomes that. Whoops, meant to write y. So that's the slope of the tangent line. In other words, dy dx is equal to minus 4x over y.
Now we just plug in the points, right?
Huh? So what is it at the point 1 comma minus
1? Positive 4.
Correct.
Cool.
That's the slope of the tangent
line. So I guess I don't have I guess I don't have as many problems as I anticipated.
Okay.
Is there any way we could do a half hour?
Sure. Yeah, no, that's fine. That's originally what I had you scheduled for. And
yeah, but then
I wanted to do an hour, so half hour is fine.
Okay.
Most of this implicit differentiation is, let me give you one just to give you one that's a little different.
All right.
What makes this different is that the previous problems we've had, we actually could have solved the equation for y, and then we could have explicitly differentiated.
Right.
The beauty of implicit differentiation is there's all kinds of equations that you can't solve for y, like this one. Notice I have no way of solving for y. You can't isolate it. You can't solve it in terms of x and numbers. However, I can implicitly differentiate it. So let's go through this. The only reason I wanted to show you this one because it involves the product rule also.
Oh, okay.
What's the next term?
See, I don't really understand what to do when I get to the combined terms that are,
Okay. The product rule is the first term times the derivative of the second plus the reverse.
Okay, so it should just be x times 1 times y prime, right?
Correct.
Or times y prime.
So I'll label it y prime, okay. Plus the rest of the product rule, let's put it in parentheses just so we're clear.
Y.
And that does not get followed by a y prime.
Yeah.
Because we were taking the derivative of x, not y. Okay, so the second term is actually 1 times y. You only follow it with a y prime if you're taking the derivative of the y.
Yeah.
And then finally,
plus 2y times y1.
Times y prime, yeah. You don't want to get in the habit of calling that y1.
Yeah.
Okay. Now, what?
Well,
we're trying to solve for y prime.
So you'd subtract the 2x.
Okay. The way I like to think about this is I'm going to put every term that has a y prime in it on the left, everything else on the right. Okay, don't need those parentheses. Erase. So here's our two terms that have y prime in. I'm going to leave those on the left.
Mm-hmm.
And you can guess what the next step's going to be.
Yeah.
We're solving for y prime. Fact. In other words, this is a mid-level implicit differentiation problem, which always involves factoring it at some step.
Oh.
Okay? In other words, factor out the y prime.
Oh, that's right.
Leaving behind what?
X plus 2y. And you just divide that?
Yeah. And then you just divide by that coefficient. And you've solved for y prime. Now, if they wanted the slope at a given point, you would have all of those points. In other words, you have your x and your y, and you'd substitute.
Okay.
Okay? And that, incidentally, cannot be simplified. Okay, what else do you have?
All right. This one is find the average rate of change with respect to x on the interval 2, 4, where y equals x squared.
How do we get average rate of change? What is average rate of change? Another word for it.
Slope, right?
Yeah, slope. Slope is what? What's it?
Rise over run.
Rise over run. That's the thing you should always remember about slope. If you remember nothing else about it, it's rise over run. So in this particular problem, what's the rise?
4.
Actually, if I graph this function,
Oh, I see what you're saying. Okay, never mind. It's
the
2.
rise is the change in the y value.
Oh, sorry. I was looking at the points, not the...
So here's the point 2.
Right.
There's the point 4. And here's a really important concept in calculus. Let's change this. Instead of calling it y, I'm going to call it f of x. And there's a reason why f of x is so much superior. What is this point right here on the f of x axis?
It's y equals 2, I guess. But...
Well, no, it's f of 2. That's what that point is. What is this point up here? That's f of 4.
Okay.
And we can plug it in. F of 2 is 4. F of 4 is 16. You see that?
Yeah.
But using this notation is critical when you get to integral calculus. In other words, figuring out what the y value is, even in differential calculus, you'll remember the way you got derivative was f of x plus h minus f of x. That's the rise. And the run was x minus h minus x, or just h. Or x plus h minus x, rather. And so this terminology you want to get really comfortable with. And what is the rise? If we fill in the numbers, what's f of 4?
4. What? Okay.
When you figure f of 4 is all you do is substitute 4 for whenever you see it.
Oh, geez. Okay. All right, 16, duh, obviously.
Minus what? F of 2.
4.
So that's the rise. What's the run?
And then run is just the same concept.
Correct. This is the run, this distance right here.
Okay.
Okay, this distance right here is the rise.
Oh, okay.
If we
Yeah.
want the average rate of change, basically I can draw a straight line between those 2 points, and whatever the slope of that straight line is our average rate of change.
Okay. All right.
Okay, and that ends up being
All right.
6.
Yeah.
12 over 2. So
All
that's
right.
the average rate of change.
Yeah.
Okay. Now, they probably want the instantaneous rate of change at the point 2 and probably the instantaneous rate of change at the point 4. No?
Actually, doesn't say that.
Okay. Well, if we did want it, in other words, that's what calculus is all about, is
Yeah.
instantaneous rate of change. Well, I would want the or the slope of that tangent line. Well, the first derivative is 2x. So now if I wanted the slope at 4, I would plug in 4 here and the slope would be 8. So this slope is 8. If I wanted the slope at 2, it would be 4.
Right. Okay.
Okay? So turned out that the average rate of change was halfway in between that, which is certainly something you would expect if you looked at the graph.
Yeah.
But that's the difference between precalculus and calculus. Precalculus cares about average rates of change. You rarely speak about average rates of change in calculus. Calculus is all about instantaneous rates of change, which you can't get from precalc. Because rise over run is 0 over 0.
Right.
So you have to use calculus to figure out instantaneous stuff.
Okay.
Okay.
All right. Yeah.
What else?
This one we don't need to solve, but I just wanted to know, if you thought this problem was a Calc BC problem.
Okay.
A projectile is shot upward from the surface of the Earth with an initial velocity of 120 meters per second. What is the velocity of the object after 5 seconds?
This is not a Calc BC problem.
It's not? Okay.
No. You have the height at any point in time, we'll call it h of t,
Okay.
is equal to minus 16 t squared plus the initial velocity times t plus the height at which it was fired from, which apparently is 0 if it was fired from the Earth.
Yeah.
So there's the function. Now, they didn't give you this function?
No. So that's why I was wondering if it would make it a Calc BC problem just based on that.
It's not a Calc BC question.
Okay.
Usually, almost always, they give you the function.
Yeah.
Is equal to the height. Now, if they were to give you some initial conditions, we could probably come up with this.
Right.
In other words, notice that if the initial velocity is 120, and I want to find the position,
Okay.
it's 120 times t, right? If gravity was not a factor,
Yeah.
then after, what was the question? What's its velocity after what?
After 5 seconds.
Okay, so after 5 seconds, if it was going 120 the whole time, it would have gone 600 feet.
But it wouldn't be going up.
Right, because it's going to slow down. But this is a position function. That's the height at any point in time. Okay,
right.
And you get velocity from taking the first derivative of position.
Oh, okay.
So this is actually a fairly easy Calc AB problem.
Huh.
Now, if you want to know its velocity after 5 seconds, you want to take h prime of 5, which is minus 160 plus 120 minus 40. What does that mean?
Well, I guess that would be where
Is it going up or down?
slowing down 40 per second.
Oh, it's going down. In other words, in our model, velocity going in that way is positive, but velocity coming this way is negative.
Okay.
So by coming up with a negative answer, we know that this projectile has gone up, reached its height, and is on its way back down.
Oh, okay. All right.
And that's why it's minus 40. In other words, if we wanted to find at what time it reaches its height, we just need the vertex, right? That's a parabola. So we could find the time that it reached its height rather easily. Yeah, minus b over 2a is minus 120 over minus 32, which is not quite 4, but a little less than 4. So 3 and change. So it reaches the vertex after 3 seconds and change, whatever 120 divided by 32 is. Which means after it reaches its vertex, in other words, if the ball is going like that, it's coming down everywhere after that. In reality, it's going straight up and coming right back down, so it's hard to show it graphically, but and that's why we usually talk about projectile motion with parametric equations rather than a single equation like this. But this is pretty useful for determining where it reaches its height, how high is it, and what time does it hit the ground. In other words, it's going to hit the ground when this is 0, right?
Oh, yeah.
Yeah, so just plug that in for 0 and solve, and that's when it hits the ground. But in terms of questions about its velocity, at any point in time, just take the first derivative. And if you wanted to know what its acceleration was at that point, take the second derivative. The second derivative would be minus 32. Well, guess what minus 32 is? That is the acceleration in feet per second due to the force of gravity from planet Earth.
Right.
So if you knew that, we would be able to work backwards to get this function.
Oh, okay. That's interesting.
Okay? But you would have to know that the acceleration from gravity is minus 32 because it's down. And then you integrate it to get to this. In other words, if this is the velocity function, the position function is the antiderivatives of this.
Oh, okay.
This would be the antiderivative of this.
All right. Okay. All right. This makes a bit more sense now.
Okay.
Yeah.
Good to go, or you got any last questions? I'm never. If you want to go 5 minutes over, I don't care. You know, I mean, we don't need to go
I think that's
precisely a half hour and precisely an hour. So
yeah, we got to all my questions on that.
Okay.
So
cool.
Yeah.
Friends, have a good one. I will talk to you next time.
All right. You too.
Bye-bye.